Okay, hello everyone. Thank you for listening to this presentation. Today we are going to talk about the enabling full stack QoS with I/O priority. I will co-present with Abhinav Sharma. He is a software engineer working in the storage team from Facebook. I am a storage engineer with a focus in hardware design. So in this talk, I will cover the hardware part and Abhinav will cover the software or application part. This is today's agenda. I will give you a quick overview of Brascaya, which is a storage server platform used in Facebook. Then I will talk a little bit about the latency management challenge for Cloud HDD. We will present the device level, some of the device level test results, and some of the application level test results. At last, we're gonna call to actions. So Brascaya is actually was introduced in OCP in 2017. It has been serving our fleet for more than 3 years right now. It is our latest disaggregated storage server and JBOD. We have 2 storage nodes, each with 36 drives in a single system. So this leverages the 1P server monolith and the NICs. It is a modular design. We can actually very easily switch between like warm storage and cold storage. This page shows the components of Brascaya. Actually, we have the cable track in the middle, and then also the bus bar in the back for the power. Besides those 2, every other components we have a pair of them for each host. So we have the storage controller card here, and we have the computer card here, and the NIC at the both sides. So actually, this is a virtual version of the presentation. We don't have a booth right now, but please feel free to visit OCP website to check our spec. So as I just mentioned, the Brascaya was HDD-based storage server. So modern hard drives could have very, very high capacity, like 16, 18, or even 20 terabyte. But the performance stays at the same level for quite a few years. This poses a great challenge for today's application when we use this kind of high capacity hard drives in our fleet. So it reflects in the below aspects. Basically, applications target efficient resource utilization with intermixed workloads. With high capacity hard drives deployed, the I/O demand across the fleet is increasing. Sometimes we could see like there's a disk utilization P50 could be as high as 70%. And also modern applications all have like multi-tenant features. This kind of feature have to provide strict isolation and service level agreements. So in this case, when we experience like some of the spiky low priority workload, they could hugely impact the latency for high priority workload. So this requires complex application sites to do some I/O scheduling control. We have to limit the queue depths. This kind of shallow queue depths have to be maintained at the device level. There are some efforts before in the OCP in the past years to try to resolve this kind of issues. One example is the fast fail rate. This fast fail rate has been developed in OCP and has already been standardized in T10, T30 spec. So basically what the feature is doing is like whenever we see the I/O could not be served with certain amount of time, we can basically abort this kind of I/O, return the status to the host so that we can seek in other disk to serve this kind of I/O. We also discussed the latency management policies, and many of the system makers facing similar challenge, and they also show interest in exploring the I/O priority feature. So in Facebook, we do have some latest findings. We are facing some new challenges when we explore this feature. So we would like to share in this presentation. This page actually shows us the device level test results. there could be different implementations at the device level. We could either target to achieve better I/O density. That means we can target for high priority I/Os. We want to have high IOPS per terabyte. We can either target to achieve better latency. We can set a target latency for certain group of IOs, so that for this group of IOs, we always prioritize on them and try to achieve the better latency on this. But there are still some challenges over there. We actually experimented with some of today's implementation. We saw the result is promising, but there's still some unexpected part of it. In the chart here, I'm showing the read latency, the P99 read latency for different workload. We experiment with two workload. One is the mix blocks, which is basically we mix in the small blocks with large blocks, and we try to prioritize on the small blocks. And also we test with the pure small blocks and see how much latency gain we can get out of it. So in this case, the tier 1 is high priority and the tier 2 is a lower priority. And then we have 50-50 allocation between tier 1 and tier 2. So by prioritize on the tier 1, look at the chart, you can basically see with the read latency, the P99 read latency has greatly reduced for mixed workload by 70%. And then if we go to a low priority workload, the latency has increased by 1.5 times. So this is actually very promising. With this kind of feature, we can reduce the latency to a big extent. And then when we test for the small blocks, we saw a different result, right? We gain, like, the latency reduction is around 50%, but for tier 2, we see a huge penalty on the tier 2 latencies, 10 times. So we kind of, the good part is like we are able to see latency gain for tier 1 and with some penalty on the tier 2. And the unexpected part is the penalty on the tier 2, it cannot be, the application basically cannot determine or cannot expect, it's not in a deterministic way. So our call to the industry is like, we would like to work with the vendors to clearly define the target latency so that we can have this kind of priority achieved in a deterministic way. In the following slide, I'm gonna pass to Abhinav to talk about the application level experiments.
Hi all, this is Abhinav. I'll cover how we basically added this IO priority support in the application. So our current storage application is a multi-tenant application, and it uses different priorities for different users which are having different kind of workloads. Some are end-user interactive, some are bash workload, and end-user interactive can be considered as highest priority. And batch users can be anywhere from higher, medium to lower priority, and usually background and internal repairs and all that stuff is low or lowest priority. Usually all these requests on the application side go through some variant of priority queue and some sort of in-flight control and deadline scheduling before these are actually scheduled to kernel. So we only have controls of certain amount from our scheduling, but once it is scheduled to kernel, we don't have enough controls. And we don't want to do too much strict in-flight rate limiting on the client side, because that might lead to some resource inefficiency, and we do want to maintain certain amount of queue depth on the device so we can get some sort of resource efficiency there. So usually applications would require conversion of these kind of application level priorities to IO priority, which kernel or device firmware understands, and we need to pass it along with each request. So the one caveat that we had was that older kernels didn't have good support of passing priority per each request. You can do it with IO nice per process per thread, but didn't have like enough controls where you can just say like this request has this much priority while sending it down to the kernel. But good thing is we had the latest kernel 5.x, which provides a new interface called IO ring, which allows you to pass IO priority per each request if you're using IO ring. So we use that for this testing, and we were able to pass. We were able to translate these application priorities to the IO priority which device can understand. Next slide. So these are the application level results that I will go through. So from higher level, x-axis, you can assume that's our P99 latencies. And then, y-axis is our P99 latency, and x-axis represent the load condition between different tenants. So as you can see, there are 4 splits here shown by the dotted line. And in each split, left one is the tenant 1 workload, and right side is the tenant 2 workload. And the blue bar is for the case where the IO priority was disabled, and orange is basically when the IO priority was enabled. So there are different, these 4 split represent different load conditions that we put these different tenants into. So first split was basically when tenant 1 had a high workload, and tenant 2 also has a higher workload. Split 2 had like tenant 1 with higher and tenant 2 with lower, similarly the other cases. And tenant 1 was our highest priority workload, which you can translate to, let's say, end user interactive workload. And tenant 2 was comparatively batched workload or a lower priority workload. So as you can see here, let's say from split 1, when we enabled the IO priority, we had about 60% latency gain for the highest priority tenant 1 workload. And then tenant 2, which is the lower priority workload, got penalized by like 189%. And similarly, as you'll see in each split, tenant 1 shows significant gains in the latency, while tenant 2 is getting penalized, but that penalty is kind of non-deterministic. So in some cases, we have all these SLAs for each of these tenants, and in one split specifically, the T1 low and T2 low, and then T1 high and T2 low kind of workloads, we saw in some cases there was this penalty impact. It can lead to SLA miss of lower priority tenant. So the main thing from here is that we want to achieve these target deterministically. If higher priority workload starts completely overloading, that doesn't mean like T2 doesn't get its enough share, and it gets penalized a lot so that it can miss its own SLA. So these are the kind of things we were testing against, which application mostly cared about. Next slide. So yeah, so main challenges here were that one, that we didn't have enough support in how we are setting up all these priority support from different hardware, and we basically want to deal with like setting these kind of commands or priority targets and all these things for different hardware differently. We basically need a standardized way for setting all these things. And then also we didn't have good IO priority levels, so we only we tested this, we only had just 2 priorities, which won't exactly cut it for our use case. We at least need like 5 priorities, or at least 3 or 5 priorities, or even more can be useful. But 2 priorities is something where we cannot put our highest versus our batch workload versus our background workload. So those were the main concerns which we had like while testing this. Next slide. So yeah, so as you've seen, like this can be a really useful feature for from application perspective, and the main call to actions for hardware vendors and system makers are that we need to have a standardized way for different kind of hardwares to set these kind of IO priority features, and then we need a clear definition of what it means what it means for different priority to get different kind of latency, or as you mentioned, different IOPS per terabyte. How do we define that, and if that can be defined in a consistent way? And we basically need to for this to work across different hardware generations, because we may be using different sorts of drive, and we cannot have our cluster with some having this feature disabled, some having this enabled, and all those kind of stuff. So this basically needs to be standardized across different hardware, different drives, and needs to support different levels of priority so that it can be useful on the application side. So I will stop the recording here, and we can take some questions from you.
Okay, so everyone hear me? Q&A session. I saw a few questions from the Q&A chat group. I'm gonna address some of them. So number one is asked by Thomas about the will dual actuator or multi actuator have with the latency. If so, by how much? Actually, the answer is yes. The IO project we discussed today is try to have the latency issue whenever the hard drive in heavy workload or deep queue. So when we have more actuator than one, actually the other actuators can help solve other IO when the IO is stored. So it's gonna help the latency. But the second question is like, if so, by how much? It is hard to answer the question because it is not linear relationship between the latency and the how many IOs in the queue. But I can answer this question in another way. So the multi-actuator or dual actuator, let's say dual actuator, if we have, ideal case, if we have twice of the workload, that means could mean like twice of the IOPS or twice of the QoS. We target to achieve the same latency with this kind of heavy workload in dual actuator drives. The second question is, we are earlier discussed enterprise storage project address some of the latency issue. This is also from Thomas. Yes, I have mentioned a couple of projects we discussed in the OCP. Some of features actually targeted to address this latency issue. One example is the fast failure rate. It is not directly to address the latency issue at the device level, but from the host level. It is kind of like when we expect the command not going to be served in a expected amount of time, we're going to be able to, the device is going to be able to return a error, a status update to the host. The host actually can cancel this IO so that it can try to read the IOs, read the data from other devices. So this feature will also help to address the kind of latency issue or IO store issue in hard drive work. So there are a lot of discussions in the OCP community about this, how we should address that. We also have been discussing about IO priority for past month or if not year. But we didn't get to a complete solution yet. But I really welcome, if everyone is interested in this project, I do really welcome people to join in our OCP storage community. There's a third question asked by Michael. Let me try to read the question first. There are a couple of them in there. So, what are some examples of actual high priority workloads in FB environment? And in certain data correlated to high priority rates? If so, what is expected mix of high and low priority data? Wouldn't it make sense to tier high priority data to SSD instead of trying to manage it QoS and HDD? I'm gonna try to, I'm not sure if Abhinav is available right now. I try to pass this to Abhinav.
Yeah, I can answer this one. So So there are certain workloads for which we do have it on SSD, like database accesses and stuff. But let's say it's not always true that all the higher priority reads are correlated with the data. So we have some warehouse data on which people are running batch workloads, and people are also running interactive queries, which are higher priority. So for those kind of workloads, data is on HDD, and we do some kind of like caching into memory and SSD for higher priority accesses and stuff. But as I mentioned, like data is not strictly correlated to the priority itself. And then on that same data, you can be doing some batch query, interactive queries, or even some compaction or transcoding later on. So we still have to handle that kind of data on one medium. So in those kind of cases, this feature is really useful. We do have higher level tiering where we have SSD level clusters itself for some distributed databases accesses and stuff, for which we handle it differently. But for this particular case, yes, we do have data on which different kind of priorities are working.
Okay, thank you.
Young, you want to add something?
I think that's good enough. Thank you. Yeah, there are some more questions coming. The first question asked by Paul: what are examples of the changes you would like to see to T10 to T13 committee? Actually, yes, as we mentioned in the presentation. So number one, we actually prefer the vendors to converge in defining what kind of target performance we want to achieve by using I/O priority. This is gonna help us to get kind of expected performance when we will try to turn it on or set it high priority to one workload over the other. So as the data showing in the slides, both at the device level and the application level, we kind of see a diverse performance gain between all kinds of different workloads. So this is very, very hard for the software layer to manage this. So that's one expectation. And another change we also expect possibly from the committee is like right now there are only very limited levels of priority. There are only two, and usually at the application level to define the priority, we usually define multiple levels, like 5 to 7 levels. If there's any chance, we can kind of define more levels in the SATA or SAS stack. That's gonna be very, very helpful. One more question. So from Paul, it's like he asked, QoS-based SATA SSD are not common and are closer to the cost of HDDs. Have you considered those devices? Yeah, so we actually, I mean, in fact, we're actually looking for all the options, all the opportunities, and different kind of devices to use in our storage servers. We didn't see. We not only look at the cost, we also look at the performance and the reliability, all kinds of stuff. We have continued keep evaluating new storage solutions, but right now we don't have a close plan to see. I mean, how the QoS SATA SSD could replace HDD in the short term. And one more question from Patrick. There are new features under development at T10, T13. Did you test and use these features? I'm not sure what we are to the new features, but we're interested in look at the stuff. I'm gonna try to what